Alright, physics fans, welcome to our last video of this series. Today we're going to just go over a couple of review questions to make sure that we're feeling good about the upcoming final. Remember, I have made it a deal that if 85% of you complete your course evaluations, I'm going to bump up your final exam scores for 5%. For everyone. So at the moment this means that 7 more students need to step up, fill out your course evaluations, and take them. Now the other thing to mention is that the finals for our class, if you are in the 11 a.m. section, your final is at Wednesday, December 15th from noon to 3 p.m. If you're in the Tuesday section of this class, your final is if you're in the 12 p.m. section of this class, your exam is on Tuesday from noon to 3 p.m. However, if you're open on either one of those, I think it's fine if you show up and take your exam, because I'm around, it's the same exam. Okay, so in our last video, I spent some time trying to get you on the path towards your first 2 units, and then we spent a little bit of time on the homework. Today we're going to try to go over our last 2 units, our magnetism and waves, and then we're just going to touch quickly some of our light material just to make it make it a little bit more solid. So what have we already gone over? We already went over the ideas of electric charge, electric field, electric potential. So you should be confident using Coulomb's law, having positive charges attract negative charges, have positive charges repel other positive charges, and have negative charges repel other negative charges. So being able to pick those directions on the forces. You should be able to be comfortable with the ideal that forces, electric forces, can either be parallel or anti-parallel to electric fields at a particular position. So this is an electric field caused by all of those electric charges at other places in space. Then this is a force that's applied on a particular charge with a charge of Q on it in coulombs. This is in coulombs, this is in newtons per coulomb, and this is in newtons. And finally, you should be comfortable with the idea that you can get the electric field from, so Coulomb's law, be comfortable with that. Force on a point charge, be comfortable with that. And then especially calculating E from V, being able to get the electric field in a particular direction is how much did the potential change over how much did the position change minus. And so the electric field is pointing downhill. It's pointing from high potential to low potential. And potential here is in volts. So volts per meter is an equivalent unit to newtons per coulomb. Okay, what else did we talk about last time? We talked about resistors and capacitors in circuits. We talked, for instance, about how if you have a V equals IR, a resistor, and it allows energy to leak out of your system. It's putting energy into the environment, and so the power that's in watts. A watt is a joule per second. Joule is a unit of energy. The amount of power is how much current is going through a particular voltage when that voltage drop is happening over the length of the resistor. Okay, so that was our lesson here. We can talk about energy loss by a resistor. And of course, we have to be a little bit careful to make sure we've got our units all lined up. Our volts, our V is in volts, our I is in amps, which is the same as a coulomb per second, and then our resistance is in ohms. The other thing that we had in these early Unit 2 types of circuits were capacitors, and capacitors store energy because they have a plus Q on one side, on one plate, and a minus Q on the other plate, and that causes there to be an electric field inside of this, which it takes energy to make a non-zero electric field. Okay, so the amount of charge that is stored on that capacitor, and remember this is it's talking about plus charge and minus charge, depends on the capacitance of the capacitor and the voltage that's being applied. So you can connect this up to a battery, plus minus battery of some voltage, and that would allow you to charge up that capacitor. And we also talked a little bit about how RC circuits you could connect it to a battery to charge up the capacitor, and it would take a certain amount of time to do that, and the amount of time is relative to R times C. Okay, and here again Q is in coulombs, and capacitance, it's confusing because the unit coulombs is a different thing from the C that's in a capacitance, but the unit of capacitance is farads. Okay, now today we are going to do Unit 3 and Unit 4. Unit 3 was on magnetic fields, magnetic forces, and induction. Now, this was a very difficult unit for a lot of people, and it's because magnetic forces act in such a funny way. In our electric forces, our electric fields, the electric force is either just parallel or anti-parallel to the electric field. But with a magnetic force, you've got a v, the speed of the particle, and a b, the magnetic field, and the force is not in the direction of the particle direction, and it's also not in the direction of the magnetic field. It's perpendicular to both of those. And so what we used to represent that was our right-hand rule. Okay, so our finger is going, our index finger is going in the direction of the current, our middle finger is going in the direction of the magnetic field, and they create a plane because you've got two vectors. Your two fingers are each representing a vector, and then your thumb is the third vector, that force that's perpendicular to both of those, that's sticking out of the plane. Now, what's confusing as well, just in the same way that electric charges can both create electric fields and are acted upon by electric fields, electric currents create magnetic fields and they're acted on by magnetic fields. So we had a couple different examples of magnetic fields that were created by current distributions. Our fundamental rule for this in magnetostatics was called the Biot-Savart law, but I haven't even put that on here because it's kind of tricky to use, and I don't want you to worry about it on your test. The magnetic fields that you are responsible for are the magnetic field of a long straight line. So that's a different right-hand rule where you have your thumb pointing along the direction of the current, and then your fingers are curling around the direction of the magnetic field created by that current. And then a similar rule for a solenoid. The solenoid's magnetic field inside depends on the number of turns per unit length and the current that you put through it. And remember, mu naught is a constant that you would look up. It's that 4 pi times 10 to the minus 7 in good units. Okay, then what else do we have in this unit? We had a lot of stuff. The other thing is the idea of induction. So if you have a changing current in going in an inductor, it can cause a voltage in the inductor, and the voltage acts so as to go against the status quo. Well, rather, let me say it another way. It acts to maintain the status quo. So if you have a magnetic field going in this direction, the induced voltage will try to keep the magnetic field pointing in that direction. And so we call that Lenz's law. And we'll see that in a couple slides. Okay, so let's just look at one of these examples that asks us to practice the right-hand rule. Okay, so it says a beam of protons is sent horizontally down the axis of a tube to strike a fluorescent screen at the end of the tube. Okay, so let's just draw in our V. So there's our protons moving down the beam path. On the way, the protons, okay, I didn't edit this question very well. Proton. Okay. The reason I did this is I changed it to protons is that I think I don't want to add in an extra layer of complication here when we're just practicing. Okay, so on the way, the protons encounter a magnetic field directed vertically downward. Okay, so our B is down. Okay, so this is the V it's going over here, and our B is going down. And then it says the spot on the screen will therefore be directed upward, downward, to the right as seen from the proton source, to the left as seen to the proton source, or not at all. Okay, so I want you to practice now using your right-hand rule. Your index finger is in the direction of the current, your middle finger is in the direction of the magnetic field, and your thumb is in the direction of the force. So the way I've drawn it in this picture, it would be V cross B gives you F. So in this picture, the F would be into the page. And if you were looking at it like this, there's your proton source. Into the page would then be to the left as seen from the proton source. And so that's all okay. On the exam, I would recommend drawing this sort of a picture, because if you have this right and then say right or left wrong, I'm going to give you credit for the question. Okay, here's another type of question like this. It says two parallel long wires carry the same current and repel each other with a force of F per unit length. If both these currents are doubled and the wire separation tripled, the force per unit length becomes. Okay, now, in this problem it says two parallel long wires carry the same current and repel each other with a force F per unit length. If both these currents are doubled and the wire separation tripled, the force per unit length becomes. Okay, so if they're repelling each other, they must have currents that are going opposite directions. If they have currents that are going the same direction, they pull together. But that's not really the important point here. You have I and I1 and I2, and they are each experiencing a force pushing them apart. Okay, now it says, what happens to this force if you double the, so you have some R, and it's asking what happens to that F if you double each one of these currents and then triple the distance between the two wires. Now, a good way to think about this is that if you have this sort of problem, what's happening here is that you have a magnetic field from the first wire. If we're just concerned about the force on, for instance, the second wire, the magnetic field from the first wire acts on the current in the second wire to create the force that's acting on it. Okay, so we can figure out what the magnetic field from the first wire is pretty easily by using our equation for the magnetic field of a long straight wire. Mu naught times I1 over 2 pi r, and that r is just going to be the distance from this wire because that's the distance at which it acts on that second wire. And so the magnetic force on that second wire would be just, I'm going to be a little sloppy with the directions because these are all perpendicular, so we get to treat these as just multiplying. So then my force would be current, and so the current that we would worry about there is the I2, that's the wire that's being acted on, times the length times the magnetic field that's acting on it, which is from the first wire. So this would be mu naught times I1 over 2 pi r. Okay, so here the force that's acting on it is going to be whatever length it's acting on times mu naught, and then it's going to be over 2 pi times I1 times I2 over r. Now the question asks, if both of these currents are doubled and the wire separation is tripled, the force per unit length becomes. Okay, so this is a force per unit length. If you want to divide both sides by L, there's your F over L. Now, if I change those currents, that F prime over L, the changed force would just be, so mu naught doesn't change, that's a constant, 2 pi doesn't change. Now it says if both of these currents are doubled, okay, so for I I'm going to put in 2I, so 2I1, 2I2, and the wire separation is tripled. So in place of that R, I'm going to put in 3 times R. Okay? And so this would give me 2 times 2 over 3 would be 4 over 3 times what we just had before. Mu naught over 2 pi times I1, I2 over R. Okay? So this would just be 4/3 times that original force. It's not too bad if you write it out, but it's probably not one that you could just guess without doing a bit of work. Okay, so then just to make sure that we are understanding, what is the difference here? How does the direction of the electric field relate to the direction of the electric field on a charged particle? How does this change for magnetic fields and magnetic forces? Do these answers depend on whether a particle has a positive or negative charge? Okay, so if you have an electric field that's in a direction and you put a plus charge in that electric field, the force is going to be in the direction of the electric field. If you put a minus charge in that electric field, the force is going to be opposite, because Q, if it's negative, it gives you a negative of the direction of the vector. Okay, so that's your electric field. On the other hand, for our magnetic field, if let's say we have B in this direction, and we have a plus charge with, let me try to make that a little bit better, plus Q, and our V in that direction. The key thing to remember is that V cross B would give us a force that is out of the page in this case. And so the force would be neither in the direction of V nor the direction of B. It's in fact going to be perpendicular to both of those. But if we had a V and a B for a negative charge, it would be opposite that. So minus Q, B, and V, we'd have a force that was going into the page. Okay, so yes, these answers depend on whether it's a positive charge or a negative charge, and it's a little bit easier for electric fields than for magnetic fields. Now, the last thing that we talked about in this magnets unit, we spent quite a bit of time thinking about how a changing magnetic field is associated with a voltage around a loop. So, for instance, in this problem, we talked about how the voltage was associated with the loop. Essentially, it looks like it's trying to maintain the voltage, the magnetic field that's already inside of its belly. So, as that magnetic, as this loop enters the magnetic field that's pointing into the page, it's going to try to have an induced magnetic field that's pointing out of the page and cause a current that's going in this direction. But once that magnetic field is inside, that loop is inside of the magnetic field, this magnetic field inside of the loop is not changing, so the current is just 0. And then once the magnetic loop, once the wire loop is leaving, it tries again to maintain the status quo, which is a magnetic field into the loop. But but to maintain the magnetic flux through its middle, it would have induced Faraday induction that's causing a current in the other direction. Okay, so it says you're looking at the direction of the magnetic field in a specific region as shown. A square loop is moving from the left to the right at a constant speed. Which one of these graphs below shows the behavior of the current, if any, as time passes? Well, your magnetic flux is steadily increasing and then is not changing at all once it's inside of that. So that would accord to this, and then your current would go in a different direction as it's leaving, where the magnetic flux through the center is changing in a steady way. And so this would be our best option. Okay, now putting these together is the painful thing, but I think it is good because it helps us to remind ourselves. We're combining vectors, we're adding electric forces, we're adding magnetic forces. So let's take a look at this. This is one of the short answer questions, so I have given you a review that has multiple choice questions. Those multiple choice questions are similar in content, but not in not the same questions. The short answer questions are very similar to the ones that I'm going to put on the test, just with the numbers change. So I would definitely advise you to spend some time working through these questions. So here it is. It says a proton gun fires protons with a speed of 5 times 10 to the 5th meters per second, pointing east. Okay, so I'm going to just draw this, my north, east, south, and west. So my V is going to be going in the east direction, so that's my plus x direction if I've drawn my axis like that. To the west of the gun, 0.5 meters, a long wire carries 4 amps of current pointing north. Okay, so I'm going to draw this distance is 0.5 meters. And I have a long wire here where I have I equals 4 amps. Okay, so this is going to create a magnetic force on that particle. This wire has a current, so the current is going to set up a magnetic field. The magnetic field is going to create a magnetic force. Okay, now it says, and 0.7 meters to the south of a gun sits a static electric charge. Okay, so here's our 0.7 meters, 0.7 meters, and this has a charge of minus 2.5 microcoulombs. So Q equals minus 2.5 times 10 to the minus 6 coulombs. We would like to figure out what force acts on the proton and in what direction. Okay, so we've drawn the situation here, including the implied direction of the electric field and magnetic field. Oh, okay. So let's figure out what directions our electric field and magnetic field going to be. Okay, I'm going to try to just clean this up a little bit. So there's my 0.5 meters there. Here's my 0.7 meters. There's the charge, and we know that if this is a proton, the Q on that proton, so let's call this Q2, the Q on Q1 would just be E. It would be that 1.602 times 10 to the minus 19th coulombs. All right. Now, what direction would our electric fields and electric forces at this point be pointing? Well, this is a negative charge, and this is a positive charge. So the electric force is going to be pulling this charge towards the minus charge. So this is plus, that's minus. And that is also just the direction of the electric field. It's the direction of the electric force, it's the direction of the electric field. On the other hand, if we look at this picture, and I use my right-hand rule for currents, I put my thumb in the direction of the current, I put my palm in the direction pointing from the current to the point of interest where my proton is sitting, and then I curl my fingers, I can see that the magnetic field would be pointing into the page right here. Okay, and so if I wanted to find out what direction, so here I've already listed what direction my electric field is going to be pointing. It's going to be pointing down. If I want to figure out what direction my magnetic force is pointing, I'm going to have to use my V cross B equals F. All right, so my index finger is going to go in the direction of V, my middle finger is going to go in the direction of B, and then my thumb is going to go in the direction of F. V cross B is F. So if you do that, you'll find out that the force on this particle from the magnetic field is actually pointing north. Okay, so the electric force is pointing south, the magnetic force is pointing north, the magnetic field is pointing up, the electric field, pointing down. The electric field is pointing south along with the electric force. Okay, so if then we want to get plug in our numbers, part B asks what's the magnitude of the electric force on the particle? We found out what direction it pushes. Part C asks what is the magnitude of the electric force on the particle, in what direction does it push, how much total force acts on the particle. Okay, so part B, you want to find what is the magnetic, let's make sure I have that correct. What is the magnitude of the electric force? Part C, you want to find out what is the magnitude of the magnetic force. And then part D, you're going to essentially add up these forces. So if FB is pointing in the plus Y direction, and FE is pointing in the minus Y direction, this would be your F net is going to be FE minus FB. Okay, so how do I find that force of the electric field? Well, I can use my Coulomb's law, which is going to be K times Q1 times Q2 over R squared. Okay, so that is going to be your 8.99 times 10 to the 9th newtons times meters squared over coulombs squared. And then I've been given the two charges that I care about. One is 2.5 times 10 to the minus 6, and the other one is the electron charge. So this one would be 1.602 times 10 to the minus 19th coulombs. The other one would be, let me just look again, 2.5 times 10 to the minus 6 coulombs. And then our R would be the distance between those two charges, would be 0.7 meters. Okay, so down here I would be 0.7 meters squared. So that should give me an answer that's in newtons. On the other hand, for my next one, I'm going to have my I would have my I, let me put it in terms, it's going to be the force on a particle, so it's going to be Q times V cross B. Okay, so the Q that is being acted on for my magnetic, by this magnetic field from the wire is this charge right there. Okay, so I know the Q is going to be my 1.602 times 10 to the minus 19th coulombs again. I know the speed of that, I know the speed of the charge, 5 times 10 to the 5th meters per second. Okay, and then I'm going to take that times B. I can treat the cross product like a multiplication because the V and B are perpendicular to each other. And how do I find the B? Well, I'm going to use my equation for the B from a long wire. So it would be mu naught times I over 2 pi r. Okay, so that would be 4 pi. So I'm going to just put this here. You can do this calculation on your own. 4 pi times 10 to the minus 7th in good units times I would be the current in amps, 4 amps, over 2 pi, and then I'd have to put in R in meters. So that would be 0.5 meters. Okay, so that's this number in Tesla that I put in there. So take this times this times this. And then you're going to get a number for your force from the magnetic field, a number for your force from the electric field, and then you can take a difference, and that would give you your net force. Okay, so there's no real tricky step in here. It is very direct, but you know, putting it all together does require us to shake some cobwebs out of our head. Okay, so that's magnetic fields, magnetic forces, magnetic induction. Whew, a lot of stuff. All right, and now we are back to our new stuff. So let's just remind ourselves, what have we been talking about recently? We've been talking about AC circuits, how you have to connect how not just the resistor but also the capacitor and the inductor, how they change the current in the circuit. So we have what we call the capacitive reactance and the inductive reactance, and they combine in this quantity called the impedance, which tells us how the current and the voltage amplitudes change. And we also spent a lot of time working to connect that description of our oscillating AC circuit. We did a lot of background filling with our returning to our simple harmonic oscillator and traveling waves and all that. Okay, so let's start out at our simple harmonic oscillator. So our good example for this was just a block on a spring that is going back and forth from the equilibrium position, and it's moving the fastest in the middle, and it goes between minus x max and plus x max, and this distance we call the amplitude. Okay, so in simple harmonic motion, let's see which one of these is true. The acceleration is greatest at the maximum displacement. Well, the acceleration is dependent on the position. That is one of the strange and interesting things about this system that's very significant. Greatest at the maximum displacement, well, the minus sign makes that a question, but I'm going to say that's a maybe. Let's see, are any of the rest of these true? The velocity is greatest at the maximum displacement. No, at the x max and minus x max, the v equals 0. Here we have our v max, our plus or minus v max, depending on whether our block is going forward or backwards. So this one is wrong. Period depends on amplitude. Well, doesn't seem to. It seems to just be independent somehow. So that of course depends on your model. But in the simple harmonic oscillator, that is not true. Period is independent of amplitude. Acceleration is constant. No, it's constantly changing depending on what part of your cycle you're in. Acceleration is greatest at zero displacement. Also definitely not true. Okay, so you use your process of elimination in doing a multiple choice question like this, and you can figure out which one is the best answer. Another thing to just remind yourself is, how does all of this nomenclature work for waves? A here, for instance, is your wavelength. The D, not B, is your amplitude, and so on. So I would recommend just going ahead and taking a look at all of those things. So it says this plot shows the displacement of a string as a function of time as a sinusoidal wave travels along it. Okay, so that's another thing to remember, is that we had two different graphs that look really similar, but they're telling you different things. One was your position versus time graph, which looks like this, and the other was your displacement of string versus position graph, which also kind of looks like that. And so it's just a tricky thing that either one can apply depending on what the question is. And in a sense, you can think of your wave as comprised of an infinite number of little of simple harmonic oscillators at each point on the rope, for instance. Okay, so which letter corresponds to the amplitude? Well, in this case, it would be D. Okay, now another topic that we talked about with waves was how one wave traveling one wave direction and another wave traveling the other direction through the same medium can interfere with one another so as to create a series of nodes where you have a larger amplitude, and antinodes which are fixed and not moving. Okay? And so in this question it says, standing waves are produced by the interference of two traveling sinusoidal waves, each with a frequency of 100 Hertz. The distance from the second mode to the fifth mode is 60 centimeters. Okay, so I have a bunch of nodes. 1, 2, 3, 4, 5. Let's say that's 6. And you have a standing wave that looks something like, if I took a snapshot at a moment in time, it would look something like this. If I took a snapshot at a different moment, it might look something like that. But the nodes are the places where the standing wave, where the medium is not experiencing any displacement. Okay, so it tells me the distance between the second node, right there, to the fifth node, right there, is 60 centimeters. Then it asks the wavelength of each of the two original waves is. Well, the thing to realize is that between the nodes you have 1/2 wavelength. So I have 1/2 wavelength, 1/2 wavelength, 1/2 wavelength. So this 60 centimeters is equal to 1 plus 1 plus 1 is 3/2 of the original wavelength of the two waves that are traveling in opposite directions. And so if you go ahead and find your wavelength, it's going to be 2 times 60 divided by 3, so 120 divided by 3 is 40 centimeters. All right, so what else? So in terms of our waves unit, we didn't spend a lot of time on the Doppler effect, almost none. And so I won't be testing you over that. The only question I put on your review says, okay, we've got a stationary source emits a sound wave of frequency f. If it were possible for a man to travel towards the source at the speed of sound, he would observe the emitted sound to have a frequency of. Okay, now in this Doppler effect equation, the reason why students sometimes have trouble with it is that it has the speed of the detector and the speed of the source. So in this problem, your detector would be the man who's listening to the sound, and so if his speed were just v, the speed of sound, then your shifted frequency would have to be frequency times v plus v over v plus, and then our speed of our source would be 0, and then that would just be 2 times the initial frequency. Okay, so that's how to get it through the equation. On the other hand, it seems like you could possibly get this one even without the equation, because it's a source and you're going towards it, and as you go towards it, you're experiencing more waves per second, and so the frequency would have to go up. These are all smaller. 0 is small, f over 2 is smaller, 2/3 f is smaller than f. 2f is the only one that's bigger than f, and infinity seems a little unreasonable. So there you go. All right, now the last part of our waves unit, we did touch a little bit on how to incorporate alternating voltages into circuits. And so the main result of this was that we had a generalized quantity called the impedance, that's Z, that's sort of related to the resistance, in that instead of having V equals IR, we would have V equals I times Z, but it's not at every moment. It's that we're relating the amplitudes of your oscillating current to the amplitude of your oscillating voltage. Okay, and so this depends on a couple different things. In this circuit, which has a resistor, an inductor, and a capacitor, okay, so your R is 50 ohms, your L is 0.2 henries, and your capacitance is 150 microfarads, so that would be 150 times 10 to the minus 6 farads. Okay, then what you have to do to get this impedance is take R squared plus XL squared minus XC squared. These are your capacitive inductive and capacitive reactances, and just add them up. Use the formula. so it turns out this is not too hard to do, because you can go ahead and solve for your XL. The only reason why it's tricky is because it depends on your XL and your XC depend on the frequency, and they depend rather on the angular frequency. So our angular frequency, we're given a frequency of 50 Hertz, So that would be 2 pi times 50 hertz, the number of radians per second. Okay, so if we want to look at what our XL is, it would be 2 pi, it would be that omega times L, so it would be 2 pi times 50 hertz times 0.2 hertz, or sorry, 0.2 henries. And then our capacitive reactance would be 1 over 2 pi times 50 hertz. And then our capacitance in farads, 150 times 10 to the minus 6 farads. Okay, and you can stick these numbers in. You can get values XL and XC, and I did that before this video started. So your XL would be around 62.8 ohms, and then your XC would be 21.2 ohms. And then now I can use this, those values and put them in here to this expression for Z. So it would be square root of R squared 50 ohms squared plus 62.8 minus 21.2, and then square that. Okay, so if you stick this all into your calculator, you should find a value that is right around 65 ohms. Okay, and so this is we need to make sure we're distinguishing how this is different from resistance. This is different from resistance in that you can't use it in a P, P equals V squared. You can't use it in an expression to find out how much power is being used by this circuit. In that case, only the resistor is dissipating energy into the environment still, but the impedance is telling you how much current you're going to get out. So this was important when we were thinking about all sorts of power applications for alternating current systems. All right, and finally, we're up to our last section, summarizing light. So we talked last time about how light has particle and wave-like types of qualities. The wave-like qualities being, of course, that you can get these interference patterns. Let's see. Which one of these is not true for electromagnetic waves? They consist of changing electric and magnetic fields. No, that seems true. They travel at different speeds in vacuum depending on their frequency. No, that seems false. They transport energy. No, that's true. They transport momentum. Yes, they do, through the pointing vector. They can be reflected. Yes, that's what a mirror does. Okay, so they all have the same speed in vacuum, which is right around 2.998 times 10 to the 8th, or 3 times 10 to the 8th meters per second. That's the speed of light. So if we want to talk about the wavelengths of different light waves, we could use our phase velocity. V equals wavelength times frequency. Okay, and if we want to find the frequency for something with a wave with a wavelength of 3 centimeters, so this would be 3 times 10 to the minus 2 meters, we could use frequency equals speed over wavelength. And so the speed of light is around 3 times 10 to the 8th meters per second. This is 3 times 10 to the minus 2 meters. And so then that would be, our 3's would cancel. This would be 10 to the 10th hertz. and 10 to the 10th is the same as 10 to the 4th times 10 to the 6th hertz, or 10,000 megahertz. 10 to the 6th hertz is megahertz. All right, looking good. All right, just about there. All right, remember Snell's law tells us that one of the reasons that light bends at an interface is because its effective speed in that material changes. So if you go from air to water, for instance, light slows down. Let's look at this example. It says, as light goes from one medium to another. Okay? So it's coming in at an angle. It says it is bent away from the normal. So there's your angle in, and there's your angle out. This angle 1, and there's your angle 2. Angle 2 is greater than angle 1. Then, let's see, it asks, what happens? As the speed increased, dispersion must occur. The second medium has a higher index of refraction. No change in speed has occurred. Refraction has not occurred because refraction means bending towards the normal. No. If it's bending away from the normal, the bigger angle goes with the bigger speed. So V2 is bigger than V1. This is faster. Okay, so this would be like going from from water to air, for instance, something like that. Or people don't like to think about water being up here. How about going from glass into air? You're looking through the sunroof or something like that. Okay, so the speed of light has increased. Yes, it is that. The second material has a higher index of refraction. No change in speed. No, refraction has not occurred. No, refraction has occurred. That's what it means for light to bend. Okay, and one last one. All right, remember, if we have light, unpolarized light go through a polarization filter, half of that light gets filtered out. If polarized light goes through a second filter, how much light gets filtered out depends on the relative angle of the polarization vector of the initial light and the secondary polarizer. So for instance, if this angle is 0 and you have two polarizers that are absolutely lined up, the second one should not absorb any extra light. Okay, now the only reason why this question is being tricky, it says this diagram shows 4 pairs of polarizing sheets with the polarizing directions indicated by dashed lines. The 2 sheets of each pair are placed one behind the other, and in the front sheet is illuminated by unpolarized light. The incident intensity is the same for all pairs of sheets. Rank the pairs according to the intensity of the transmitted light, least to greatest. Okay, so remember what happens here. What happens is that after the light goes through the first polarizer, then the second polarizer, this angle that we worry about is relative to the angle of the first polarizer. So for instance, in this first case, if I have the first one at 60 degrees back here, and my second one, then so my unpolarized light comes through, it becomes polarized along this direction, and then my secondary polarizer is over here. And so if this is 60 degrees and this is 60 degrees, 60, 60, the sum of all of those angles, if it's a flat line, has to be 180 degrees, so this angle also must be 60. Okay, and so you can do that sort of analysis for each one of these. The angle in this case would be 60 degrees that we would worry about. Here we've got 45, 45. The angle here would be 90 degrees. Here we've got 75, 75, okay, 85, 90, so that's 15, 15, so that would be 30 degrees would be the angle between these two. And here we have 60, 60, 30, 30 plus 45 would be 75. Okay, now remember what cosine looks like. Cosine goes from big down to 0. From cosine squared goes from 1 to 0, from 0 to 90. So really all we have to do is we have to, it says rank the pairs according to the transmitted light least to greatest. So the least light is going to get through when the two filters are perpendicular to each other, when there's a 90-degree angle between them. So our least is going to be 2. Okay, so I can scratch off the ones that don't start with 2. Then we have 4. Then we have 1. Then we have 3. Okay? 2, 4, 1, 3. Okay, so we did this problem. All right, now I can't claim that I have done all of the problems on your review, but I do want to commend to you that the rest of the studying here is your job. Please use your equation sheets during your practice tests. The multiple choice questions that I've given you on your review sheet are very similar to the content of the multiple choice questions that you will see on your test. The short answer questions are the same format even that you're going to see on your test. So knowing these questions intimately when you come in on your exam is the way to do really well on this. Okay, so please fill out your course evaluations, and I will see you